describe is a very, very useful algorithm for finding the modular exponentiation, or finding the value b to the n mod m very, very quickly. And this is really important to do in cryptography, specifically in RSA crypto systems, to not use an excessive amount of memory to compute b to the n mod m, when b, n, and m are all large integers. First thing you might say is, well, it's why not just calculate b to the n and then take the remainder of it upon division by m. And the problem with this is that even for relatively small numbers, exponentiation gives a very large number, as you know from orders of growth. So, for example, if you look at 3 to the power 644 mod 645, and I'm not recommending you by any means try this by hand. If you go through and use a calculator to solve for this, what you end up getting is that the value of this is going to be 36, but it's going to have a quotient of this right here times 645 plus 36. So you can very, very clearly and obviously see that this is not something that you're going to want to go through and do by calculating b to the n and then dividing it by the modulus. However, this algorithm for fast modular exponentiation is very cool. And the idea here is the following. We're trying to compute b to the n mod m, and what we do is we start by expanding the exponent n in base 2. And what this gives us is something very nice. B to the n is going to be b to the a naught plus a 1 times 2 plus a 2 times 2 squared, all the way up to the maximum integer in our expansion of n base 2. And we know from basic algebra, this means that b to the n will be b to the a naught times b to the a1 times 2 times b to the a2 times 2 squared times b to the a3 times 2 cubed times b to the a k minus 1 2 to the k minus 1. Which is the same thing as b to the a naught times b squared to the a naught to the a1 times b to the 2 squared to the a2 all the way to b to the power 2 to the k minus 1 to the power a k minus 1. And now what's important here is that you remember that if we're in base 2, for each value ai is going to be either less than or equal to 1 or equal to 0. So ai will either be 0 or 1. Because ai is an integer. And not only that, but for our rules of modular arithmetic, or from our properties of modular arithmetic, b to the n mod m is going to be, because of this equality, b to the a naught mod m times b squared to the a1 mod m all the way to b to the 2k minus 1 mod m, or to the power a k minus 1 mod m, and this entire thing will be mod m. And let's make a little bit more space here so this looks a little bit nicer. So the idea here is to just kind of progressively build larger and larger and larger powers of b to the power 2 to the power I, right? Because this is going to be b to the 2 to the power 0 to the a naught, b to the 2 to the power 1 to the a naught, b to the 2 to the power k minus 1 to the a k minus 1, and so on and so forth for every single term in this multiplication. And here's where we get to the heart of the algorithm, because each one of these a values is either going to be 0 or 1. We're either only going to have to compute 1 mod m, right? B to the a naught, if a naught is 0, will be 1 mod m, and if a naught is non-zero, then we just have b mod m. Same thing here. If a1 is 0, then we have to compute 1 mod m, which is just 1. And if a1 is 1, then we have to compute b squared mod m. So the algorithm quickly goes through and computes b mod m, b squared mod m, b to the 2 to the 2, which is b to the 4 mod m, and so on and so forth, all the way up to b to the power 2 to the k minus 1 mod m. And with these values, then you can directly go through, very easily multiply them, and then get the modulus of the result. So in our example that we worked on before, we want to compute 3 to the 644 mod 645. Our b here is 3. n is 644, and m is 645. $644 is equal to 101000 0100 in base 2. And so from this binary expansion, we see that the only non-zero digits in this binary expansion are a 2, which is 1, a 7, which is 1, and a 9, which is 1. And so the number 3 to the 644 is going to be equal to 3 to the 2 squared to the power 1 times 3 to the 2 to the 7th to the power 1 times 3 to the 2 to the 9th to the power 1, from the formula that we showed in general holds before. And now starts the process of going through and determining each of the expressions, b to the power 2 to the power I in this expansion. And the real trick here, right, is that 3 to the 2 to the power k is the same thing as 3 to the 2 to the power k minus 1 times 2, or 3 to the power 2 to the power k minus 1 squared. This is really the trick that we use here, and is the key thing that kind of makes this a really fast procedure. Because we start off, we have the 3 to the power 2 to the power 0 mod 645 is just equal to 3 to the 1 mod 645, or 3. And from this, then we have that 3 to the power 2 to the power 1 mod 645 is this squared, which is 9 mod 645. And so if we continue on, we then have that 3 to the power 2 to the power 2 mod 645 is going to be equal to 9 squared mod 645, or 81. And this is one of the values that we need to compute our product. We need 3 to the power 2 to the power 2, because a2 is 1. So we have to store this value right here. And the next value is 3 to the power 2 to the power 3 mod 645, which is going to be equal to 81 squared mod 645, which is 6,561 mod 645, which is 111. Continuing on, you get 3 to the power 2 to the power 4 mod 645, which is 111 squared mod 645, which is going to be 12,321 mod 645, which is just equal to 66. Next, 3 to the power 2 to the power 5 mod 645 is going to be 66 squared mod 645, which is going to be 4,356 mod 645, which is 486. And 3 to the power 2 to the power 6 mod 645 is going to be equal to 486 mod 645. Sorry, 486 squared mod 645, which is going to be 236,196 mod 645, which is 126. And then the next one is 3 to the 2 to the 7 mod 645 is going to be 126 squared mod 645, which is equal to 15,876 mod 645. And note that 3 to the 2 to the 7 is one of the numbers that we need. This value is 396. So we have to store this value. And 3 to the 2 to the 8th mod 645 is equal to 396 squared mod 645, which is 156,816 mod 645, which is just 81. And the last value, 3 to the 2 to the 9, we have to store this value, mod 645 is equal to 81 squared mod 645, which we actually already calculated at a previous step. This is 111. And so we need to store this value here. And so from our formula in modular arithmetic, we have that 3 to the 644 mod 645 is going to be 81 times 396 times 111 mod 645. which is a multiplication that we can break down into two parts. First, we'll do 81 times 396 mod 645. This is going to end up being equal to 471. And then our answer is going to be this 471 times 111, because this mod 645 is 471. So our answer will be this times 111 mod 645, which we calculate out to be 36. Which is equivalent to the calculator remainder calculated earlier at the very beginning when we considered this example right here. But it avoids the hassle of going through and actually computing this big quotient right here, which would take much longer to do if you were to do this by hand. So even though this example is a little bit long, right, there are a bunch of steps to this procedure. I think it clearly shows this algorithm and how to implement it, and the usefulness of it in terms of calculating these large modular exponents. The last thing that I want to cover in this lecture is a very cool example to the field of what's known as pseudo-random number generators. Basically what a pseudo-random number generator is a deterministic random bit generator. This is also known as a deterministic random bit generator, or DRBG. And typically the way that these functions is, in general, all that this is an algorithm for generating a sequence of numbers whose properties approximate the properties of random numbers. So this is a very important thing in a lot of different applications, and specifically for, like, say, simulating probabilities using the computer, simulating various games using the computer. This is an extremely important process to figure out. And the problem here is that you can ask yourself the question: how do you generate a sequence that appears to be random, or is for all intents and purposes a random sequence? When it comes to hardware, you could kind of maybe focus on physical properties that are random, that appear to be random. But the idea here is that for our random number generator, an actual random number generator, this is something that constructs an actual sequence of numbers or symbols that can't reasonably be predicted better than by random chance. So the idea here is that we need to think about effective ways of generating pseudo-random numbers. There are many practical uses of sequences like this, but the idea here is that we're going to consider one very specific algorithm and kind of look at it in general for constructing such sequences. And this is called the linear congruential generator. Or LCG for short. This is an algorithm that yields a sequence of pseudo-randomized numbers with a discontinuous piecewise affine equation. And in mathematics, linear equation is an equation of the form y is equal to a times x. An affine equation is not linear, it's y is equal to a times x plus c. And this is the type of equation that a linear congruential generator uses, ax plus c. So this is actually, it uses discontinuous piecewise affine functions. And the remainder upon division by some large modulus. So I really want to emphasize here that a lot of times, mistakenly in certain texts, this type of equation is called a linear equation. In the case of c equals 0, right, this is a linear equation that's used because you just have a times x. But it's really important to point out here that mathematically speaking, in general, the type of function that's used here is an affine function, not a linear function. So this sequence is actually relatively straightforward to write down. The sequence is given by x naught, which is called the seed, or the initial value that we put in to the generator, and then the sequence is xn plus 1 is equal to a times xn plus c mod m. Where xn here is the sequence of pseudo-random values m is the modulus A is between 0 and m is the multiplier C is the increment and x naught is the seed, or starting value of the sequence. If C equals 0, like I said before, this is called a multiplicative congruential generator, or a lemma RNG. Which was published in 1951. Whereas the linear congruential generator was published in 1958 by Thomson and Rottenberg. So what I want to do is show you a number of different examples of this pseudo-random number generator to see how well it works. And sure enough, as you might expect, the choice of A, C, and M are very, very, very important here when implementing this algorithm, and we'll see why very shortly. So let's start by first considering the values 9 for m, so m equals 9, a seed value of 0, a C value of 1, and an A value of 4. So xm plus 1 is going to be 4 times xn plus 1 mod 9. So we're starting with the seed value of 0. The first value that gets produced is going to be 0 times 4 plus 1 mod 9, which is 1. The second value is going to be 1 times 4 plus 1, which is 5 mod 9, which is 5. Next value is going to be 21 mod 9, which is 3. Next value is going to be 13 mod 9, which is 4. Next value is going to be 16 plus 1, or 17 mod 9, which is 8. Next value is going to be 33 mod 9, which is 6. The next value is going to be 25 mod 9, which is 7. Next value is going to be 29 mod 9, which is 2. And the next value is going to be 9 mod 9, which is 0. You see then, at this point, we start repeating the sequence. So for this small value of m, we can't really get many random numbers, so to speak, because the sequence just starts repeating itself over and over and over and over again. If we code this algorithm up in Python and do a plot, we can kind of help ourselves see, what's actually going on here and why what we're getting is not truly random. And if you only consider these numbers, it seems like it's kind of random. So to visualize this, in general, what we can do is construct our sequence. X0, X1 is the first output, X2 is the second output, and so on and so forth, all the way up to Xm. And what we do is we divide each one of these by the modulus. So we consider X0 over m, X1 over m, X2 over m, and so on and so forth, all the way up to Xm over m. In this sequence, R0, R1, all the way up to Rm, of these values are all going to be random numbers, specifically random rational numbers that are between 0 and strictly less than 1, because each value xm is strictly less than the modulus. So what we'll do here is we'll generate a sequence of pseudo-random numbers using a good algorithm specifically this is the random number generator in Python, because the code that I'm going to use and that I wrote is in Python, and specifically I'll use the package NumPy in which the random number generator routine produces sequences or matrices of pseudo-random numbers between 0 and 1 using combinations of a bit generator function to create random sequences and a generator function to use those sequences to sample from different statistical distributions. A bit generator is an object that generates random numbers, and a generator is an object that transforms sequences of random bits from a bit generator into sequences of numbers that follow a specific probability distribution. And for all of the applications that I've used it, for all intents and purposes, it works very, very, very well. And specifically, what we're going to do is compare this sequence to our algorithm that we've done so far. So the sequence of pseudorandom numbers I'm going to plot out as points, Ri star, Rj star. These are the points generated by that good algorithm. And then what we'll also do is generate the sequence R1, R2, R3 up to Rn from before, from the linear congruential generator. And then just compare the two results and kind of discuss the results. Specifically, what we'll do is we'll plot the points R1, R2, R2, R3, all the way up to Rn minus 1, Rn. And the idea here is that if the sequence of numbers R1 to Rn is truly pseudo-random, these points should behave just like the good algorithm, and should also have a random type distribution. So we'll look at this example right now. Where it'll become immediately apparent that we're not getting a good result. Because if we open up this plot right here, we see very clearly that the NumPy or Python random number generator is doing a good job, whereas our LCG is falling very, very flat. Specifically, right, because of this periodicity here, I mean, you can expect it to repeat. If you try and do more values, you're only going to get these values of this LCG, and it's not random at all. Specifically, all of these lines are right. This is kind of like there's a line of points right here, and right here, and this structure is typical for certain bad values of the LCG. It's not surprising that we're getting lines here because of the affine function definition of the LCG. Right, we're getting basically like a bunch of different lines that are corresponding to essentially a bunch of points modulo m that all obey this y equals ax plus c, or y equals ax in the case of a linear LCG. So the idea here is that when you take ax plus c mod m, you're just going to get a bunch of lines in n-dimensional space. So this is definitely a problem, and it's a problem that in some sense we can kind of fix if we choose better values of A, C, M, and our seed. We're always going to have this, but for clever choices of A, C, M, and the seed, we're going to get that this problem is going to be fixed. But it will always be an issue, especially for higher dimensional random sampling. So as we increase the number of the dimension, we're going to run into this problem again and again, and we have to be very, very careful with A, C, M, and the seed x naught. So for the next example, we'll consider M to be 2 to the 32, A to be equal to 3, C to be equal to 0, and the seed to be equal to 1. So we're going to try a larger value of M. Hopefully this ends up helping us. And just as you may have suspected, this is also not a good result here, where the stars here are the random numbers or the random points generated by Python's NumPy's built-in random number generator, and again we're getting that this LCG is actually completely determined. Its values are completely determined by values lying along lines in this two-dimensional space. Ideally, what we want is for the blue points here to be distributed randomly all over space, but this is not happening because of the relationship between x and y in this formula right here. Specifically, I guess, in the formula for this example, x n plus 1 is equal to a times xn, c is 0, mod m. So this is not good. Also, I increased the number of points here to be 1,000. So the n here, maximum value of n, is 1,000. So you can clearly see that these values of a, c, and x naught are clearly not working. What we'll notice is that if we increase the value of a, this is the same thing as, in some sense, increasing the slope of each one of these lines, we get something interesting. Specifically, that the slope of the lines in the xy plane becomes larger because, of course, we're increasing the a value. And the hope here is that if we can increase this a value to a large enough value that still is less than m, the distribution of these points will appear to be random, or actually be a good random number generator. So this is what we get when we increase a to 13. And you can clearly see that we're hopefully gonna, as we increase the value of a, get exactly what we want. And sure enough, for a equals 111, if we get up to this value of a, the plot that we're seeing here is definitely not distinguishable by my eye from the plot of stars. So these are the circles here compared to the stars, and we're getting something that appears to be a truly random distribution. And just one final example here for a equals 555, we're seeing that very clearly this is doing a pretty good job. Oops, and I just noticed here, this there's a code, there must be a typo in my Python code, which I'll fix. In the title here for the plots, this should be 555. This should be 111. It should be 13. This should be 5. And this should be 3. What I think happened was I must have had to put X naught in the code where I meant to put A. So I apologize for that, but the idea here is that we're clearly seeing that for large values of A, even with C equals 0 and a large value of M, we're getting what we want. Now, be careful here if we consider A equals 500. Things are not going to go as well as we would hope. And this is demonstrated by the following two plots, which is two separate runs, and you see very clearly that you're not getting a good result at all because you're not getting a randomly distributed sequence of blue dots. So the reasoning here is not because A is large that this is working right here for 555. The reasoning is that A is co-prime with M. So we're also seeing this is the same thing with 111 and 13 and so on and so forth. So let's define what we mean. First we'll define what a prime number is. A prime, or an integer p that's greater than 1 is called prime if the only positive factors of p are 1 and p itself. Also, we have that positive integer s that is greater than 1 and is not prime is called composite. And so for the definition of coprime, we have that two integers, A and B, are called coprime. This is also known as relatively prime or mutually prime if the only positive integer that evenly divides or is a divisor of both of them is 1. And so these two properties, specifically the coprime property and the relationship of C, A, and M are directly, in some sense, what's determining the success of this algorithm. We definitely know that M needs to be large, and there are many different possible choices for large values of M that make sense to guarantee that it's coprime to the value C and possibly to the value A. There's also more going on here as well in terms of factoring M possibly if M is not prime. There's a lot of different things and different things that you can analyze. The simplest possible case is the lemma random number generator to analyze, which is C equals 0. But the idea here is that all of these things can be analyzed and kind of summarized, make sure that you're using the best algorithm. And I'm not going to get into this. I just wanted to present this example and show it as a very cool example of one of the things that we can do with modular arithmetic. But thank you very much for tuning into the lecture today. I hope you had a fantastic day and that you learned something.